Hello students, welcome to lecture 6 of your course Elements of Discrete Mathematics. In this course, we shall mainly discuss the properties of the lattices. Mainly we discuss properties of lattice, then certain definitions of some particular types of lattices and certain exercises for your practice. So let us discuss some properties of lattices. So in this theorem 1, we are going to list these properties and proving these properties in view of the definition of lattice. So before the statement is this theorem, let us have a look at this notation here. You can see this has a notation that if we have a lattice L, we define this operation meet and the operation join. These are given by x meet y is equal to greatest lower bound of x and y, or we also call it as infimum of x and y. Exactly in the same manner, if we have this operation x join y, then it is equal to the least upper bound of x and y, and you can also say that this is the supremum of x and y. So now we state the properties here in theorem 1. If L along with this relation is a lattice, then for any L3 elements A, B, C belongs to L, the following results holds. Number 1, A meet A equal to A, and parallelly we can say A join A equal to A. So this property is called idempotent property. So we can say in every lattice the idempotent property is satisfied. Similarly, this second property is A meet B is equal to B meet A. And parallelly, for the operation join, we can say A join B equal to B join A. This property is called the commutative property. Third one is A meet B. This becomes one element. Then meet C is equal to A meet B meet C. So this becomes one element. Exactly the same property, if we replace this operation meet with the operation join, we can have here. Such property is called the associative property. So this associative property also holds in the lattice L. Fourth one involves both the operations. Suppose we have A meet A join B. So here B will be absorbed in it. That is why we are calling it as absorption property, and we will be having A. Similarly, if we interchange the operations, if I write here join and here meet, so we get this situation. So again in this case also this B is absorbed and this quantity is equal to A. So this operation is called absorption operation. Or you can say this property in fact is called absorption property. So this absorption property also holds in a lattice. These results, the proof of these results can be obtained using the definition of join and meet and the properties of lattice. In fact, a lattice, as we have already discussed in our last lecture, that if a set L is lattice, then first thing is that it must be a partial ordered set. That means it must satisfy four properties. Number one, three properties first. Number one, a reflexive property. Number two, antisymmetric. Number three, transitive property. It becomes partial ordered set. And once it becomes the partial ordered set, then we check pairwise. For every pair of elements, the supremum must exist and infimum must exist. If these conditions are satisfied by this set, then it becomes a lattice. So keeping in view all those properties, we can prove all these four results. So let us see Here we shall prove the results only for the one case, that means for the case of join, for the case of meet operation here, and similarly the operations can be obtained for this part. So here we shall discuss the proof of this part only. We shall prove for properties for meet operation. The steps are similar for the join operation. The proof of first property, you can say. What is meaning of A meet A? A meet A means, according to the definition, this is in fact the infimum of A and A. Infimum of A and A. So when A and A is repeated in this set, so we can write it as a singleton set. In fact, if we have a singleton set, then its supremum and infimum is same thing. So we can say this is equal to A. So obviously we are getting A meet A equal to A. So A meet A equal to, exactly in the same manner you write here A join A, then you get supremum, and supremum of singleton set is the same element A, so we can get in the exactly in the same manner A join A equal to A. Now the commutative property, if we have A join B, A meet B, then that is equal to infimum of AB. If we are having two elements, then we write infimum of AB, or we write infimum of BA, that is the same thing, but and you can write this thing as B meet A. So what you have obtained, A meet B equal to B meet A. Exactly in the same manner you proceed for join. You have A join B, you will write here supremum, you will write here supremum, and here it becomes B join A. So the commutative property is also satisfied for both the cases, meet operation as well as for the join operation. Now we are coming to the third property. Third property is this one, the associative property. Associative property, we shall prove A meet B meet C is equal to A meet B meet C. So actually in this case we have to deal with this part separately, and then we take the meet with A. So let us look at this. We have to prove both these things as equal. So in fact, what is meaning of this? Meaning of this, B meet C means we have to find the infimum of B and C. Once you find infimum of B and C, let that is equal to D. Then you will find the infimum of D and A. You will find infimum of D and A, and that will be some element, of course. Similarly, in left hand side, first you find the infimum of A and B. Let that is something K, and then you find the infimum of K and C. That will be something, some element definitely. Then these two elements must be equal. So that is the idea here. So let us see how we can prove these two things equal. So we are taking first B and C. We take B join C. So let this B join C is equal to D. So of course, by definition, this B meaning of B join B meet C is infimum of B and C. So D equal to infimum of B and C. And by definition of infimum, if this element D is infimum of this set, what does it mean? Both the elements of this set will be greater than or equal to D. So I can say D less than equal to B, and again D less than equal to C. Means both the elements of this set will be greater or equal to this element. This is definition of infimum of a set. Now, because you have taken this quantity as D and you wanted to find the value of this thing, you wanted to find the value of this thing here, this one B meet C, this is actually D, and you are taking meet with A. So A meet D you want to find. Let us see. A meet D. Let this thing is E. A meet D is equal to E. So what is the meaning of this? It means E equal to infimum of A and D by definition of this meet operation. So when E is infimum of both these, that means E will be less than equal to A as well as E less than equal to D. So here what we have obtained, one thing, that E less than equal to A. Here E is less than equal to D, but we have already proved here this D is less than equal to B and D is less than equal to C. So combining these two situations, this one with this one, because D is less than equal to B as well as D is less than equal to C. So I can say E will be less than equal to, by transitive property, E will be less than equal to B as well as E will be less than equal to C, because here D is less than equal to both. So this situation can be represented here. Now we can see E is less than equal to A and E is less than equal to B, and this uh, E is less than equal to C. The three things are appearing here: E less than equal to A, E less than equal to B, and E less than equal to C. How this E less than equal to C is coming from these two parts. So we can say that E is lower bound of this set. E is lower bound of this set. Now we consider F is any other lower bound of this set. F is any other lower bound of this set. So if F is also a lower bound of this set, that means this F will be less than equal to each element of this set. So I can say F less than equal to A, F less than equal to B, and F less than equal to C. So from this situation, what do we get? F less than equal to B, F less than equal to C. Now we have already considered that this D is infimum of B and C. Infimum of B and C. So infimum, in fact, greatest lower bound, and F is a lower bound of B and C, and D is the greatest lower bound of B and C. So by definition of greatest lower bound or infimum, I can say this F will be less than equal to D. F will be less than equal to D. This is the point to understand here. Further, we have F less than equal to A. Here we have obtained in the last line, you can see F less than equal to A. So now I'm considering here F less than equal to A. We have also taken that E is infimum of A and D, and F is any, F is less than equal to A, and E is infimum of this set A. Means I can write here F is less than equal to E from this. So now what we have, F is less than equal to D and F is less than equal to E. E was the infimum of E was a lower bound here. Actually, we have proved that E is a lower bound of ABC, and we have considered an arbitrary lower bound F of the same set, and here we have proved that any lower bound, any arbitrary lower bound of the set ABC is less than equal to E. So if any lower bound of the set is less than equal to this E, then I can say this E is the greatest lower bound of the set ABC, So we can say E is equal to infimum of ABC. Similarly, we can prove that infimum of means, in fact, if we have obtained this quantity, so exactly in the same manner, we can say this A meet B meet C also equal to infimum of A, B and C. Thus we can say this quantity will be equal to this quantity, right? So here we already know E was this. So we have proved the left hand side equal to right hand side. So A meet B meet C, and if we take A meet with B meet C, so this property is satisfied. So I can say the distributive property with respect to meet operation is satisfied in a lattice. exactly on the same steps. In place of supremum, if we proceed with the in place of infimum, we proceed with the supremum operation. Then we can also prove the other property, the parallel property here, that A join B join C is equal to A join B join C for all elements A, B, C belongs to the lattice L. So that is why we say the distributive property is satisfied in a lattice. Now the fourth property is in fact the absorption property. You can see this one. We shall prove this property, the absorption property. So we prove the one part here. We take A meet A meet A join B equal to A. Means we have to prove this quantity on left hand side equal to right hand side. So we can prove this property by the argument that we show that this value on left hand side is less than equal to A and A is less than equal to this quantity A meet A join B. If these two conditions are satisfied, then lattice is a partially ordered set, and in a partially ordered set the anti-symmetric property is satisfied. Anti-symmetric means if something is less than this and that again less than equal to this, then it is possible in only one situation that A is equal to A meet A join B. Means we shall proceed according to this argument. We shall prove this quantity and this inequality and this inequality, and these two will consequently give the desired proof. So let us see. I want to prove A meet A join B is equal to A, and procedure I have described here. We know that by the reflexive property that A is always less than equal to A. Further, A join B is the supremum of two elements A and B. What is the meaning of A join B? A join B is in fact supremum of A and B. And when supremum, by definition of supremum, I can say A less than equal to A join B as well as B less than equal to A join B. So we can utilize any of these, whatever is needed. So here I can say A less than equal to A and A less than equal to this quantity. So A will be less than equal to the join of these two. A will be less than equal to join of these two. So A is less than equal to A join A meet A meet A join B. So one part is done here, A less than equal to this. Now we are calling this as equation first. Again, if we know, look at this expression, A meet A join B. This is in fact infimum of A with A join B. Now you know that the infimum of these two is definitely less than equal to A. So from this, by what we have proved that this quantity is less than equal to A. So we have proved that this quantity is less than equal to A. So from 1 and 2, when these two are happening, so according to the antisymmetric property, this quantity is equal to A. So this proves the absorption law. So now the four properties of lattice are proved here. Now come to theorem 2. Let L with the relation less than equal to be a lattice in which the meet and join denotes the operations meet and join. Then for any AB belongs to L, show that A will be less than equal to B if and only if. This symbol is for if and only if. If and only if means if we consider this quantity, this inequality, with the help of this we can show this. And if we consider this part, then we can show this part. So that is the meaning of if and only if. We can have two-way implication. Exactly here, A less than equal to B if and only if A join B equal to B. So these are two important properties of the lattice. Suppose we have suppose that A meet B equal to A, and you will prove here this in this situation. You see, in the first case, A will be less than equal to B. A less than equal to B. You want to prove this thing. So A meet B means infimum of A and B, and by definition of infimum, this A meet B less than equal to B. But you are given in the statement that A meet B is equal to A. So in place of this, if you write A, so you will get this quantity, A less than equal to B. Now conversely, if we suppose A less than equal to B, then in this situation you shall prove, or you will prove A meet B equal to A. Let us see how it happens. You are considering this value, and you will prove this value. A less than equal to A. By the reflexive property, we can write like this. Now, in the statement we are given A is less than equal to B. So A is less than equal to B and A is less than equal to A. So we can say that A is a lower bound of this set AB. And you know, the lower bound is always less than equal to the greatest lower bound. The greatest lower bound or infimum means the same thing. So I can say A is less than equal to the greatest lower bound of this set, means the infimum of this set. So that is why we can write here A less than equal to infimum of AB, but infimum of AB equal to A meet B. So what you have proved here? We have proved that A is less than equal to A meet B. We have done this thing. Conversely, we can see A meet B is infimum of AB. So due to this fact, we can have two things. A meet B less than equal to A and A meet B less than equal to B. So here I am considering this part. So A meet B less than equal to A, and here we have done this thing. A less than equal to A meet B. So here A less than and here A meet B is less than. So both the opposite situations. So due to the antisymmetric property, these two inequalities gives you A equal to A meet B. A equal to A meet B. So in this part, what you have proved, first you have considered this A meet B equal to A, and we have proved A less than equal to B. Conversely, we have considered A less than equal to B, and we have proved A meet B equal to A here. So this is the situation. Exactly in the same manner, you can prove the second property, and you can try it yourself. Next, come to example 2 here. Show that the idempotent laws follow from the absorption law. So here we will consider the absorption laws and will prove the idempotent law. So absorption law, you know from theorem 1 that A meet A join B equal to A and A join A meet B equal to A. The two absorption laws are there. Now in place of, because here because we are talking in a lattice, the elements A, B, C are in a lattice. A, B, C, these A and B, these elements are in a lattice L, and in a lattice L, A join B belongs to L as well as A meet B also belongs to L, means infimum and supremum and infimum of two elements belongs to L. So obviously, if I consider it as a single element, this is an element of L, single element. Exactly, this is an element of L. Further, if this is an element of L and you take meet of this with this element, So again, the subsequent element will be in L in the lattice. So that is why, because of this logic, if we substitute A meet B for B in equation 1, means in equation 1 in place of B, because here I am already saying that A and B can be any element of L. So in place of B, if we write A meet B, so what happens here? It becomes A meet B, A join. In place of B, you are writing A meet B. We are replacing B with this A meet B. So what happens? Now this becomes the equation number 2. This becomes the equation number 2. And from equation number 2, this quantity is equal to A. So the whole quantity in this bracket is equal to A. So finally, what we are left with is A meet, and the whole quantity is A. So that gives us A meet B equal to A. Similarly, if we proceed with the second equation, means we replace B with A, uh, as in this case we have replaced B with A meet B, and if we replace B with A join B in the second equation, then we can obtain again A join A equal to A. Thus we can say that idempotent laws can be obtained from the absorption laws. Example third, for any positive integers, a, b, show that LCM of a with GCD of ab equal to a, and exactly GCD of, in the same manner, GCD of a with LCM of ab is equal to a. And of course we are talking in a lattice, because GCD and LCM, obviously we are talking in a lattice, and lattice of natural numbers. And since we are involving here GCD and LCM, then obviously we will be talking about the divisibility operation. We know that n with the relation less than equal to is a lattice, where n is the set of natural numbers, and this relation is defined as a less than equal to b if and only if a divides b. So we have already discussed the situation in detail, that with respect to this operation, the set of natural numbers forms a partially ordered set. So in this lattice, if we define the join operation and the meet operation, those are in fact A join B is LCM of AB and A meet B is GCD of AB. So applying the absorption law, we can say A meet A join B equal to A, and A join A meet B equal to A. So these are two absorption laws. Now substituting the values according to these things. So A join B is in fact LCM of AB, and LCM of AB is this quantity. And if we are taking A meet means here the GCD. So in fact this thing, in view of these two absorption laws, gives us this result. Similarly, in view of these definitions of join and meet and these second absorption law, we can get this equation. So this completes the proof, the solution of this example. Now we have certain definitions. A lattice L is bounded if it has an upper bound denoted by 1, and such that x is less than equal to 1 for all x belongs to A, and it has a lower bound denoted by 0. 0 means not the number 0, 1 means not the number 1. 1 stands for the upper bound of the lattice. That means all elements of the lattice are less than equal to this thing, and all elements of the lattice are greater than equal to this 0 element. 0, I again repeat, 0 doesn't mean the 0 number. It is denoting the element from which all elements of the lattice are greater or equal. Similarly, 1 is denoting the element from which all elements of the lattice are less or equal. A lattice is said to be distributive if this property is satisfied. X join Y meet Z means X join means this distributed means this operation is distributed with Y as well as with Z. So X join Y then meet X join Z. Similarly, if we uh, interchange the operations, join with meet, so we can have here meet and here we'll have join. Similarly in right hand side, so these two properties are satisfied, then lattice L is said to be distributed. Now the complement of an element A of a bounded lattice L with upper bound 1 and lower bound 0 is an element B such that A join B gives 1 and A meet B gives the 0. Such a lattice is complemented if every element of lattice has a complement. If every element of lattice has the complement. So clearly you can understand from this definition that we can find the complement of an element in a bounded lattice. Note one more thing. It is always not possible to find the complement of an element in a lattice. There may exist certain lattices in which there are certain elements for which complement does not exist. So if we have an element A and we want to check the existence of complement, then it must be some element B that satisfy this property that A join of this B with A is equal to 1 and meet of this element B with A is 0. Only then we can say that element B is the complement of element A. And if there exists some lattice in which each element has its complement, then such a lattice is called a complemented lattice. So based on this discussion and these definitions, you can try these exercises, and these are very simple one. You can think about these, and we have referred this book M.K. Gupta Discrete Mathematics, Krishna Prakashan, and K.H. Roshan Discrete Mathematics and its applications. So thank you.